Linda, can you hear me? Linda, can you hear me?
Yes, I can.
Okay, great. Okay, and yes, and some other people are saying they can hear, so that's good. Okay, great. I have started the recording. Okay, so we're recording, and this is tonight, so we'll wait into here. Linda, as I look ahead, I could see this being an evening where you standing ready with a calculator would be a good thing. And so we'll see how that works out. But if you could, kind of be prepared for that or something, that would be good.
You
Okay,
got it.
so thank you. Okay, so here we go then. All right. So first of all, a little bit of course maintenance or something like that. So from the cockpit, I have to say we're on course and we're on schedule. We're well on our way to completing the material that we need to. And in fact, I will say that I think we've completed a lot of it because, I posted the videos for pretty much everything, but we're going to be doing things in this, in the VCM to help you. And the first one of these is tonight. The next one is on Wednesday. That's already December 1st. And then we have two more VCM sessions. I'm going to be posting for the net people the thing in the in the testing center for those people who can do that. For those people who can't do that, we'll have to do accommodations. But anyway, so we've got 4 more sessions that we will have together. I think Linda will have some GSGs and things like that, and then we'll go from there. Now the thing that I marked with the star here, the 13th, that's during final week, and that's the evening when in the VCM we will have our our final exam will be happening in the VCM. And so that's kind of what's in front of us. So we're certainly in the home stretch. And again, this is going to be people who are doing it either in the testing center or in the VCM context. And so I do need to have people, and I'll be sending an email again reminding people to do this, but let me know if you have accommodations that we need to plan for, because I have to get that done. And you see the deal with this and the midterm accommodations just kind of drug on for a while, and that was no one's fault, but we were able to do that because midterm was around midterm, and then we had a lot of time to do that. We're not going to have a lot of time to mess around with that at the end of the course because the term ends. So let's make sure we do that. There is going to be a study guide and grace notes made available probably on the 8th is when we'll do that. And between now and then, we'll be covering new material, and we'll be doing some reviewing, but that's what we're going to be doing. The normal time at the College of DuPage, by the way, is a final exam is 110 minutes. That's an hour and 50 minutes. That's the regular time. And so on the 13th, we would meet at 6, and you would have till 7:50 to finish the exam, and that would be the hard end on that night. Okay, so that's pretty much what I have to say. I think we're in good shape, and tonight should be a productive evening as we're dealing with that. And then I always want to give Linda, and Linda, of course, can talk anytime she wants, but this is an opportunity for her to, say some things, and then we'll go to any student Q&As. And of course, the student Q&As are also always welcome, and things like that. But these are explicit times when you can say some things. So anyway, Linda, what would you? Is there something you'd like to either report or share with the students?
GSG was pretty slow tonight, so just so you guys know, that is still an option. If the GSG time doesn't work for you, then you can find me on campus between like 9 and 3 p.m. Mondays and Wednesdays, and then Tuesdays and Thursdays, then I'm there basically all day. So if the GSG times aren't working and you're still looking for some last minute help, then feel free to stop by the Learning Commons and just tell them that you're looking for me.
Okay, and that is SRC 2102, I think. So anything else, Linda?
Nope, that would be it.
Okay, I'm going to throw it open for a count of 10 or so for student Q&A, anything that people may want to do. And if you don't, have a question to ask right now, that's okay. You can always ask questions, but this is time for us to raise some of those things. So I'm starting my internal count right now. Okay, I think I see Amber's hand up. Amber, what is up with you?
You said for the final it's until 7:50.
Yeah, I
Okay,
did.
awesome. Thank you.
And that's not me, that's the College of DuPage doing that. And they have, I don't know, I actually could talk about the history of how some of this stuff came about, but it's actually not very interesting. And so, but they do have rules, and that's one of the rules, and they have a final exam schedule. And one of the things that's inherent in that schedule, and this is a good thing, is it makes sure that people don't have overlapping finals, because if you play it the way you're supposed to according to the COD handbook, then final exams aren't overlapping one with another. But if it's just a free-for-all, people making up whatever they want to do in the class, then you could have conflicts. So this is I think this is a good thing, and you got a running start to get ready for it. Okay, and whenever I get a question, I always will sort of reset my my time thing. So I'm starting my count again. So if other people have things they want to ask about, this is your time. Okay, so that's that, and we'll go on and start talking about some things. Now, this stuff really is in the videos, and we've covered some of this before, and so on and so forth. But I thought it was useful and we are going to do quite a few problems with this. And I usually have problems involving density and also pressure in a fluid on the final exam. So we're going to talk just a little bit about these things. And you should realize that these things that I'm showing you right now are pretty much the grace notes that are going to be on the final exam, because this is what they look like, because I just kind of take the end material from the chapter. So I'm going to go through a few of these things, and then we're going to work some problems, and maybe Linda will do some calculations for us so we can know what the answers are and things like that for a few example problems. And that's kind of what's going to be happening during the balance of the period tonight. So anyway, we start talking about density. I know I'm reading to you, but density is mass per unit volume. So is mass over volume, and there's different units of mass and different units of volume, and some of those things we'll have to do as we go along. But if a mass m of a material has a volume v, its density is, and this equation is one of the ones that you'll be using some certainly tonight, and that is the Greek letter rho. I know it looks like a P, but that isn't a P. That's a rho, and that's sort of the Greek R, and the way that's spelled is RHO. If you wanted to know how it was spelled, but just looks like that, and it kind of looks like a stylized P, but that's rho. So that is the density, and density is equal to mass over volume. So one realization of a density would be kilograms per cubic meter or something like that. Now, if it's different units, you want to be mindful of the units, because units matter. And one of the things we'll see in some of the problems tonight, you have to be mindful of the units and make sure that the units balance out when you're doing a problem. Now, there's another thing that's floating along that's very related to density, and it's a number that's called specific gravity. And specific gravity is the ratio of the density of a material to the density of water. So you could talk about something being, you know, denser than water or less dense than water, or if it was exactly water, the specific gravity would be 1. Now, it turns out, though, when you talk about the ratio of densities, you have the density of the material, which would be, for example, kilograms per cubic meter, relative to the density of water, but the density of water would be reflected in the same um, units, kilograms per cubic meter. So you see specific gravity if we have a problem that deals with that. And I know there's at least one problem that was looking out there that has specific gravity. So that is the ratio of these densities, and it is a dimensionless quantity if we run across that. So density will be featured in a number of these problems. Also, we have a concept that is called pressure. And I know we've talked about this before, but we're talking about it again here. And assuming the pressure is constant over the area in question, then we say that pressure, now this is a P, and it does stand for pressure. And pressure is the force, and this is the force perpendicular to the surface, and it's force per unit area. So it's force that is perpendicular to that. Now, if you say, well, what if the force isn't perpendicular to that? Then there is a component of the force that is perpendicular to that, and you're going to use trigonometry to get at that. And so that's an important kind of consideration. And I think well, there's some problems that we can probably do that just deal with this. So I'm going to race ahead and maybe do a few problems that don't involve Pascal's law. So we'll talk about density and see how we do with this this concept. So we'll come back and look at this equation, or we've already looked at this equation. And now what I'm going to do is I'm going to go and bear with me just for a minute. That's a call from the College of DuPage. Hello? Oh, okay. I'm teaching right now, so can I call you back a little bit later? Okay, but my students are wanting me to tell, well, I don't know if they're wanting me to do this or not. They probably would like for the call to last longer. But I did want to pick up, but if I can call you later after class, that would be good. I will look at it. Okay, thanks. Bye. Okay, so I'm going ahead then. That was from a College of DuPage number, and that was the reason that I answered it. Okay, so here we have a problem. Okay, and let's just look at let's look at a few of these and make sure that we understand how we might encounter this density thing. And so we're just going to talk about number 1. So you purchase a rectangular piece of metal that has dimensions 5 millimeters by 15 millimeters by 30 millimeters, and it has mass that is 0.0158 kilograms. The seller, the person who's trying to sell you this piece of metal, tells you that it is gold. And you decide that you're going to check that. So you're going to figure out what is the average density of this piece, and you're going to check to see if you're getting gold or if you perhaps are getting cheated with this. So what I'd like for you to do is, and in fact, what I'm going to do is, and Linda, I'm going to ask you to maybe remember those numbers or something like that, or at least have it there. I may ask you what those numbers are again.
You got it.
But we want to figure out if this is gold or not. And you see, every element in the periodic table has a density associated with it, and you can't fake the density, but that's what this person might be doing. So what I'm going to do then is I'm going to share my screen with you, my application screen, and we're just going to look up, and I think gold actually is, and I'm going to do like a Google thing. And so I'm going to open the Google window, or a Chrome window, I guess, and I'm going to just ask this: what is the density of gold? And I have no idea what it's going to come out. I mean, it will show me here a number. And it was supposed to give me, I wanted it to give me a number. I don't want this Oxford Dictionary. And so let me just go, I'm going to go back and ask it a different way. In fact, I am going to go to Google because I think Google will be more direct with this. Okay, that's good. And they have their Christmas decorations up. That's good too. And then I'm just going to say density of gold. Okay, now it tells me that the density of gold is, and it shows it up here, but it tells me that the density of gold is, and they're talking about copper gold and things like that. Let's see, I guess I want to have the numerical value. Here's a physics fact book, so that should give us. Okay, so the density of gold right here is 19.32, and this is grams per cubic centimeter. So it's 19.32, and this is grams per cubic centimeter. So you see, I have to have grams per cubic centimeter as my units to check to see if this actually is gold. So what I'm going to do then is now I'm going to stop sharing. And I'm going to go back to here, and I'm going to share my screen again, but this time I'm going to share a blank whiteboard. We're going to put some of these things up and figure this out. Now, what we just learned when we looked it up, and I could have given you that in the problem too, but the density of gold is 19.32, and the units matter. So this is 19.32, and this is grams per cubic centimeter. So it is mass over volume. Now, Linda, the dimensions that we had were, I think, 5 millimeters. And Linda, I'm going to just let you tell me what they are. Okay,
So
bye.
5 millimeters by 15 millimeters by 30 millimeters.
All right, now when you multiply all this stuff together, you're going to have cubic millimeters, which are not cubic centimeters. So you have to do a conversion there to do that. But okay, so if I take this, though, I will have, let's see, I'm doing some things in my head here, but I will have 75 times 30. And let me, in fact, not do that in my head. I'm doing it over here with pencil and paper. So this is going to be 0, that's a 5, and I carry 1. So that is 2250. So this is 2250, and that's cubic millimeters. So that is the volume that I have. Now, if I want to change this into centimeters, okay, I need to think about this. And a centimeter is going to be, so I need to multiply this by And if I want to have cubic centimeters, which is what I do want to do to compare that number, I'm going to say, well, I have cubic centimeters per, and this is cubic millimeters. Now, I need to think about this a little bit because a cubic centimeter looks like this. It is a centimeter on every side. So this is what a cubic centimeter looks like. I'm drawing a little cube. And what I have is that there are 10 millimeters per centimeter. So we have that, we have that. Let's see, that's the up direction, that's this direction, and this is going to be the final direction, is 10 millimeters. Okay, so that means if I have 1 cubic centimeter, then I have 10 times 10 times 10. And so this is going to be 1 cubic centimeter is going to be 10 times 10 times 10 is 10 to the cubed cubic millimeters. Now the millimeters will cancel out, but this is 10 to the minus 3 cubic centimeters. So this would be 2.25, and this is cubic centimeters. And Linda, what was the mass of this thing?
Let's see. That was, I'm getting 0.0158 kilograms. That's what was given in the problem.
All right, now these are grams though. Okay, so we got this into this, but you said kilograms. So that is, and I'm going to write down what you said. It was point zero what?
0.0158 kilograms.
Okay, so this is kilograms. But if I want to have grams, I need to change the kilograms into grams. So that means that I'm going to have to, and so I'm going to be multiplying by, and this is going to be grams per kilogram. And there are 1,000 or 10 cubed grams per kilogram. And so the kilograms are going to cancel. And I have 10 cubed. That means I move the decimal point 3 places. So this is going to be 15.8. And this is going to be grams. Okay, so now I take this number, 15.8, Linda's doing that, and dividing that by 2.25 to find the density of the substance we've got. And right away, I can see that this is not going to be, we'll get a real number from Linda, but 15.8 divided by 2.25 is going to be in the neighborhood of 7, which means that this guy's really trying to cheat you. They're giving you something that is not anywhere near as dense as gold. And Linda, what is the real number here?
About 7.02. So you were right on the mark.
Thank you. Okay, 7.02. And again, we know that this is grams per cubic centimeter. Okay, so that's a density problem. Now, this is not exactly the problem I'm asking about, but this is a kind of a standards type density problem. And so I'm going to pause for a moment or two to see if there's any questions about this one. Okay, people don't seem to have questions. So Linda, can we go back to the slideshow and let's take let's just take number 2, I guess. Now there's a whole bunch of problems here, but we're just going to do number 2. So kidnapper demands 40 kilogram cube of platinum as a ransom. But then they ask, what is the length of the side? Now this is a little bit different problem. Okay, but it's a problem that we can do because there's density equals mass times the volume. Now, one of the things to be aware of is there's a different, in fact, I'm going to ask everybody to try to do this. And Linda, why don't we give them, I'm going to suggest 3 minutes. It's, according to the clock I'm looking at, it's about 6:27. Actually, it turned to 6:28 when I did that. So let's give people a couple of minutes to do this problem, and then we'll do it ourselves. And Linda, if you could keep time, that would be great.
Of course.
Okay, so everybody's working on this problem. It's a good test for you. You're testing yourself. It's not where I take a grade or anything. So go ahead.
All right, it's been about 3 minutes.
Okay, thank you, Linda. All right, so I looked it up, and maybe you did too, but we found out that what we're looking for with platinum is, and Linda taught me how to do this, so I will just erase this quickly. So this is 21.45, and this is grams per cubic centimeter. And if you remember from the previous problem, this is denser than gold, and platinum actually is a precious metal that's even worth more than gold. But anyway, this is what we this was what we have. Now the person said that they wanted 40 kilograms, but they wanted this in a cube for some reason. And this is kind of a strange criminal wanting this way, but that's what they wanted. And so if you wanted to get back whatever the criminal took from you, you would try to comply with their demands. Okay, so this is 40 kilograms, but we know that 40 kilograms divided by the volume, if I change this to grams per cubic meter, must be 21.4. So let's change this into grams per cubic meter. And so what that means is it's 40 kilograms. So we're going to go ahead and use this conversion factor. But we need to know how many grams are here. And so we're changing this to grams. And so we're multiplying this by, we want there to be grams in the answer. Well, we've got kilograms right now. Okay, so in 1 kilogram, you have 10 to the third, or 1,000 grams. Okay, so the units now here will be grams per this, and I'm going to set this equal to 21.45. And now this is going to be grams per cubic centimeter. Now, if I were to solve this, then what would happen is that the volume, and if you just look at the units, you'd realize that these grams will cancel with the kilograms will cancel one with another. And so this will be grams per a volume. And so what we need to do then is we need to solve for this. Now this involves a little bit of algebra because this volume is in the denominator. And so what I'm going to be doing is kind of saying, okay, so this is 400, or excuse me, 40, and then there's 3 zeros, because that's what times 10 to the 3 means. Grams over V is equal to, and this is 21.45, and this is grams per cubic centimeter. And you could think of that as being over 1. And so that means to figure out what the volume is of this cubic centimeter that you're giving the person is you cross multiply and divide by V. So what I would get then is that L cubed, which is the volume, that's the length of the side times the length of the side times the length of the side, and they're all the same because it's a cube. So I'm going to get L cubed is equal to, and Linda is going to divide 40,000 by 21.4 and tell us what she gets for that, and then we're going to take a cube root. And in fact, while she's doing that, I'm going to erase my picture of the cube.
So for the volume, I'm getting 1,864.8.
Let's see, so she said 16, and was that
1,864.8.
18? One day I will be back in class again and won't have to do this, but so it is 1, and then it is 8, 6, and then there was a decimal point or something?
4.8.
4.8. But now, you see, we wanted to know, because the problem asked us what was the length of the cube, and so we're going to say that L then is equal to, and Linda's going to take the cube root of this with her calculator. And again, if you were doing this problem, you'd have to take the cube root too. And so that's what we would get. And so Linda will pound that into her calculator and tell us what the side of length is.
So that's about 12.3 centimeters.
Okay. Okay, and I suppose it depends on how big of a, carry-on thing you would have, but that's going to be about 5 inches by 5 inches roughly. Okay, so that that's actually not very big, but that actually would be worth a lot of money. So I'm going to pause and see if there's questions that anyone wants to raise. Okay, Linda, let's go back and let's look at those problems again if we can. So she's loading the PowerPoint slide, and let's maybe do one more problem. Let's just look at number 4. So I'm going to read number 4 to you. You guys do it. I'll give you about 3 minutes to do it. Then we'll come back and we'll talk through the solution. And then I think we'll move on to something other than just talking about density. Okay, so the question is, by how many newtons do you increase the weight of your car when you fill up your 11.5 gallon gas tank with gasoline? A gallon is equal to 3.788 liters, and the density of gasoline is 737 kilograms per cubic meter. And another thing that you need to know to do this problem is that a liter is 1,000 cubic centimeters. Okay, so everybody do this. Linda, how long should we allow for this? 3 minutes, you think's enough?
Yeah, that should be fine.
Okay, so 3 minutes, Linda will be marking time. And so give it a go. I think I actually told you everything you need to know. So see if you can do this. And if not, at least you'll have prepared yourself to understand the answer that we go over.
All right, it's been about 3 minutes.
Okay, excellent. Okay, so I don't know if I'll remember these numbers or not, Linda, so keep them in mind in case I need to ask for that. I'm going to share my screen with people, my application screen. Okay, and so we're getting this, and actually I should have probably shared a whiteboard instead. So I'm going to share a whiteboard instead, and then I'm going to erase the whiteboard. Okay, now I think I remember that that we had 11.5 gallons. Again, you can do this in a different way, or just doing it this way. So I'm taking the 11.5 gallons, and I'm going to change that into liters. Okay, so I know that I want gallons in the bottom because I want that to cancel out. And now what I'm going to do is I am going to put liters up here, and I think it was 3 point. Linda, help me. What, 7?
3.788.
Okay, and this is liters per gallon. So we're going to multiply those together, and when we do, those units will cancel, and that's supposed to be an L, that thing there. So that is going to be liters. Now, I really, though, want to have the answer being in, and actually, I really wish it was in cubic meters, but what I told you was that cubic centimeters, that a liter was 10 cubed cubic centimeters, but I'm going to figure out how many, that's what a liter is, so that is 1 liter. When I do this multiplication, that liter will cancel with that liter, and so we'll have cubic centimeters, but now I have to change this to cubic meters, and so to change this into cubic meters, I'm going to have to say that I want the cubic centimeters to cancel, and there are 10 to the 6th cubic centimeters per 1 cubic meter. So I need to put, let's see, I want the centimeters to cancel. So 1 cubic meter is that, and so you see, I'm going to figure out how much, what is the volume of this gasoline in that. Now this cubic centimeter cancels with that one, so this is going to be cubic meters. And Linda, I'm going to ask you to multiply these numbers across. So, and this is for the students, not for Linda, because Linda knows how to do this, but for students, it might be useful for you to think about that as 11.5 over 1. And what I would do, I don't know what Linda's going to do, whatever she does will be fine, but I have 10 cubed over 10 to the 6th, so I'm going to know that's 10 to the minus 3. And so anyway, she's going to give me a number. When she gives me the number, I know that this is cubic meters.
So once you go through and multiply all that out, then you get 0.043562. And again, that is in meters cubed.
Okay, so that is a cubic meter. So that is how much cubic meters I have of gasoline. Now, the density of gasoline was, and I think it was 737. Is that right, Linda?
Yes, it is.
Okay, so it was 737. And again, guys, units really matter. So I'm thinking this was, and in fact, I wasted a lot of time if it wasn't, but I think this is kilograms per cubic meter. Linda?
You got it.
Okay. And you might think about gasoline, and you see the water is 1,000 kilograms per cubic meter. So this is about 70% as dense as water. And that's the reason gasoline evaporates easier, and it's why actually you can smell it more strongly when you're filling up your pump. So anyway, if I'm doing this, what I would end up with doing is this would cancel with this. Now I actually used the density formula here to do that. So I'm taking a volume times a mass per unit volume. So this gives me a mass. So this is going to be kilograms, and Linda's going to tell me what this is whenever
So
she
that is about
has it.
32.1 kilograms.
32.1, and this was kilograms. So that is good to go. But now I wanted to know how much this weighs in newtons. Well, and so this is going to be 32.1 times, and this is going to be 9.8. And this is the G, okay, and this is the acceleration due to gravity. This was kilograms. So I'm multiplying kilograms times the acceleration due to gravity to get its weight, and the acceleration due to gravity is going to be meters per second squared, and of course this answer is going to be newtons, because a newton is a kilogram meter per second squared. Okay, so Linda does that, but she's going to get around 32. What is the number, Linda?
So I'm getting about 314 newtons.
Oh, okay, I was doing something really stupid. Linda is right, so that is 314 newtons. So that's how much your gas increases when you fill the tank. And you remember I told you that a newton is the force or the weight of about a really a good sized apple. And so you're actually making your car quite a bit heavier by doing this. This is like you had 314 apples in your trunk, perhaps, and big apples that you would have. Okay, so any questions on this problem? Okay, Linda, that's good. I counted and I think we're good. So I'm going to erase a bunch of this stuff. But then, Linda, take us back, please, to the PowerPoint show. And I'm going to take control. We did a bunch of density problems. There's some more there. If you wanted to practice, that's fine. But I'm going to go back because we're going to talk about some other things other than just that. Okay, but that's density. And we also have pressure is force perpendicular to area. Now that is pressure, but we're going to talk about some other things, and maybe not that right now, but we're going to go, actually maybe I should have talked about, yeah, maybe I have to go back and talk a little bit about Pascal's principle. All right, and so I am talking about Pascal's law now. So Pascal's law states that the pressure applied to the surface of an enclosed fluid is transmitted undiminished to every portion of the fluid. And so that's actually, and there's other words here, but that's actually what we're using here. And the fluid is actually incompressible. So we're going to go to a problem. And so I'm racing ahead here, trying to find the problem that I want to work with you now on. And this is a problem that I have asked on tests before. Linda will recognize it, and it's called, it's called problem 27. It's called hydraulic lift. Okay, and in fact, this is something that, in fact, just recently, I had to buy a new tire for my car. And so when I bought the car, bought the tire, they had to put it on a lift just like this. So they really were using this very technology. Okay, so but now we're saying you're designing a hydraulic lift for an automobile garage, which is where they put my tire on. It will consist of 2 oil-filled cylinder pipes of different diameters. Now I'm going to be pointing, and I think, well, maybe if I grab my pencil, I can point. Okay, so here is a guy. So I'm drawing like an arrow there. This is a guy, and he's working the hydraulic lift, but he's got this pump, and this is called hydraulic fluid. And so it is an oil-based substance, but it is not compressible. And what that means is when you push down on it, it just sends, like Pascal's principle says, it sends the pressure along. So this guy is taking, and again, this is a tiny little cylinder. This is about, let's see, it is 25 centimeters. So that would be, this is about 10 inches in diameter. So they're showing you the diameter there. So that is 25 centimeters, and that is in diameter at that point. And he can push down on that with this lever and do that. But then you got a big old diameter thing on the other side. And again, this is not to scale or anything like that, but you got a big old diameter thing and you're trying to push the car up. Okay, so anyway, so this is kind of the setup. And so you got 2 pipes of different diameters, but they're interconnected in the way that you see, and they have different diameters. So a worker pushes down on a piston at one end and raises the car on the platform on the other end. And you see the fluid that he squishes down on just goes to the other side and it lifts the car. Okay. And so you see the pressures are going to be the same. So handle a full range of jobs, you must be able to lift cars up to 3,000 kilograms plus the platform. And this is the platform right here, this thing that the car is on, and that weighs 500 kilograms because they put the car on that. To avoid injury to your workers, the maximum amount of force a worker should need to exert to lift a car that has this mass is 100 newtons. Now that's a force, and that's what this guy is pressing down perpendicularly onto that, okay? But the pressure inside the fluid is going to be the same. And so what that means is that the force 1 to the area 1, that's the pressure to the area, is the same as the force 2 to the area 2. So you see that's the important physics equation that you're using here. Okay, so so there are 2 questions. What should be the diameter of the pipe under the platform? And again, it's saying diameter. And if the worker pushes down with a stroke that is 50 centimeters long, by how much will the car raise at the other end? Okay, so that's what we have. So why don't you give this a go, Linda? Let's say 4 minutes on this because this is a different thing, and I think this is problem 27. So Linda, the students please work on this for about 4 minutes, and
Sounds
Linda
good.
will call time for us, and then we'll, and Linda I think is with us for the duration, and 7 is there helping Linda out, I hope. So anyway, we're working on 4 minutes then. So Linda will tell us, and then we'll talk through the problem. So everybody, please give it a go, think through it. And I know there's a real temptation to just say, yeah, I'm just going to text and wait. It actually readies your mind to understand the solution if you try to do this. And who knows, you might even get exactly the right answer. So that would be great.
All right, it is just about time.
Okay, great, thank you. And I'm going to go to a whiteboard then, and we'll do some things. And Linda, I don't know, there probably will be some calculations along the way. And if you can help us with the calculator, that would probably be good. Okay, so let's grab a piece of thing and let's begin talking. All right. Well, the area of that this force is on is going to be equal to pi r squared. Now, r squared is half the diameter. Okay. So that means that what we're going to have for this one thing where it was 2.5 um, uh, centimeters, or 2.5, let's see, it was, okay, so we can do that. So anyway, we will have that the force 1 over, and the area is going to be pi r1 squared is equal to the other force, but this is going to be pi r2 squared. And that is both, those should both have been squared. So I'm going to clean that up a little bit. Actually, neither one of them looks like a 2. So I will try it again. Okay, so this is r sub 2 squared. Now pi is on both sides, so that's not an issue. And I know that the thing that the guy was pushing down on was 100 newtons. And we wanted to raise a 3,000 kilogram car. And so that, and this radius is half the diameter, and I think it was 20, let's see, that was 25 centimeters. So this would be 12.5, and this is going to be centimeters squared, and this number is also squared, is equal to, and on the, and I'm putting like a punctuation mark here, that's supposed to be a semicolon, is equal to, now this is 3,000, and that was kilograms, so I'm going to have to multiply this one times 9.8, and then this is going to be divided by, and I already canceled that, so this is going to be r sub 2 squared. Now what Linda's going to do is she's going to pound this into a calculator, and then she's going to take a square root to find out what r sub 2 squared is. In fact, let's do it a step at a time though, Linda. Okay, so Linda is solving for r sub 2 squared, and she'll come up with an answer for that, and then we'll figure out what r2 is, and then we'll have some things that we can do. Go ahead, please, Linda.
So for r sub 2 squared, I'm getting about 45,937.5.
And the units on that have to be square centimeters. Okay. All right, and then she's taking the square root of that. Go ahead.
So then I get 214.3 centimeters.
And again, that is okay. And the answer that I have is, let's see. So that was 100 newtons times 9.8 is 3. Okay, so the ratio of those are 3.43. So up here you got that this was let's see, this is times 9.8. So this is 3.43 times 10 to the fourth newtons. 10 to the fourth, and those are newtons. Okay, and so we multiply and we get this in 12.5 squared is whatever that is. Okay, so now, so that means that the diameter of this would be twice that. And so in centimeters, the diameter would be 428.6. And that we're still talking centimeters. Are we okay with this? Okay, now the same amount of fluid moves, so what we're going to say is that the diameter of 1 times the area is equal to the diameter of 2 let's see, I'm trying to remember. Oh, we were saying how far did it move, right? So here we were just figuring out what's the diameter. So we have that, but now we're figuring out how far it moves. So this is the volume of fluid that got shoved by the little guy. So this is the one that's shoved by the big guy. And so what we're going to have is, this is going to be, and this is the calculation, and this is going to be the area 1 and area 2. Okay, so, yeah, and I'm just going to ask Linda to put some numbers in here. So this is going to be, oh, and they told us that the fellow pushed 50 centimeters. So we have 50 centimeters here. And so the answer to this is going to be the distance we're trying to find is going to be 50 centimeters, and this is going to be 1.25 meters divided by this number right here, and I'm using that in meters, so this is going to be 2.14 meters, and I am going to be squaring that ratio because it's pi r squared. And so, Linda, what do you get for that?
So that I'm getting about 17.1.
All right, now that is 17.1, and but now we were multiplying centimeters times square meters. Now the square meters are going to cancel out, so we're going to get centimeters, and let's see. 50 centimeters. Okay, so whenever we do that calculation, let's see, that's about 1/2, that's about 1/4, and 1/4 goes into 50. Well, it's not exactly 1/4 either. So I'm doing too much arithmetic in my head. Okay, so the answer to this should be centimeters. Wait a minute. Oh, I screwed this up, Linda. I am so sorry. That was not meters. That was 0.125. I was wondering why I was off. That is 0.125 meters because that was given in centimeters. And the other thing I think you gave me in meters. So I changed this to meters. So this is the calculation you should do. And Linda, I think the big thing that will happen with that is you probably will have 1.7, right? Or what do you get when you do?
0.17.
0.17. Okay, and that would be centimeters, and so that would be So that would be centimeters if we did that, and it would be if I did that in millimeters, it would be multiplying by 10 yet again, so it'd be 1.7 and change millimeters. Okay, so you see, you do have the same amount of work is done, but it's work that you can do. You have to push further, but you lift something very heavy, but not as far. So that's the magic of hydraulics. And again, you should be able to do this problem. Okay, so questions about this. I want to pause and make sure if people have questions that they ask them. Yes, Tatiana.
Yeah, like we have a 3,000 kilograms car and plus 500 kilogram platform there. So how
That
do
was a script. That was no.
oh,
That was me screwing up.
oh.
So this number up here. Thank you so much for paying attention. I didn't pay attention. And I think this number here actually is right, but that will change Linda's numbers a little bit. And I was wondering why my numbers were off just a little bit, and now I understand. So we should have done 3,500 here, Tatiana. Thank you for that. And okay. But then the rest of the problem, we would work it the same way. Any other questions? Okay, she says, thank you. That was good. That clarification, I guess, worked for her. Okay, no one asked any questions. Certainly you can ask questions as you work on these things and things like that. Okay, Linda, let's go back to the slideshow. And I think for the last 3 minutes, I'm just going to talk about some other slides and not necessarily work problems because I don't think problems will fit there. Again, we're in good shape. We pretty much finished off chapter 13 here. Okay, so we talked about that. Some of these concepts, though, are useful and come up in the, so I talked about Pascal's law. I'll say a little bit more here. Okay, now I stopped after I read one sentence and we worked some problems with that, but the total pressure at any level in the fluid is the external pressure plus the pressure due to the fluid. The pressure P sub 2 at a depth h below the surface then is P sub 2, h below is going to be P sub 1 plus rho times GH. Now rho is the density of the fluid, G is the is gravity, okay, and H is the depth, but P1 is the pressure at the fluid's surface. And you see there really is a pressure of the atmosphere that is pushing down on each and every one of us. And that pressure of the atmosphere really is quite a bit. It is 14.7 pounds per square inch. And that's an amazing thing. I think that's a square inch. Let me in fact check that. Just so I'm giving you the right units. I know the number is 14.7, and I'm just going to look this up in, okay, I'm going to say pressure of atmosphere at sea level, and I want to do pounds per square inch. There we go. Okay, and there it is. And you can see that I was very close to being right, that this is 14.7, and that's pounds per square inch. Now, my point that I'm making is, you see, so when I'm sitting at my desk at the Learning Commons and I have to get up from my desk, what happens is I have to shove away 14.7 pounds per square inch, and I have a lot of square inches because I'm chubby. I'm being kind calling myself chubby, but I'm chubby. So whenever I stand up, I have to be it actually is a lot of work I'm doing because I'm pushing against this pressure. Now, I am used to this pressure though, and that's why I can do it without panting too much usually. Okay, so anyway, and we didn't get very far, but now we're finished. I will have office hours later tonight. Anything else you want to say, Linda, at the end?
No, I think that's it.
Okay, so I'm going to go and let's see, I'm going to turn off the recording, and maybe I'll see some of you in my office hours. So we pretty much are finished with chapter 13. We'll go into chapter, I think 23 is the next one that we do, and we'll talk about some more boundary behaviors. And there's a bunch of videos that you could